Hello. In the previous video, we studied matrix operations. Today, we study properties of such operations. Let A and B be matrices of the same size. So we know that we can add them, we can subtract them, and we can do scalar multiplication, right? So I write in short like a linear combination of these two matrices. And if you have two matrices A and B such that the number of columns in A is equal to the number of rows in B, then we can do multiplication. A times B, right? A times B. Then the matrix AB means the product is of the size M by K. Look at this. M is this, and then here with a K. Okay. So, from the definition of matrix multiplication, you can see that actually AB is not always equal to BA, given that AB and BA exist because of this, you see? So, the matrix multiplication is not commutative. That's what we have seen from the previous lecture. But today, we'll talk more about that, okay? So let's move to properties. Suppose that you have three matrices A and B and C, M by N matrices, okay? And C and D are scalar. Then, first property, AB plus B equal to B plus A. This is commutative properties of addition. The second one, associative, A plus B plus C equal to A plus B plus C, okay? The third one, if you have two numbers C and D, you multiply with the A, that is nothing but, C, D, A. So this is associative property of multiplication, of the scalar multiplication. So the next property, one with the A is A. So remember that. What does it mean, lambda A, right? Lambda A means you just multiply all entries of A with that number. So you get lambda A, right? So when lambda is just 1, you have the same. The next property, CA plus B equal to CA plus CB. So this is distributive property. Again, right? This property comes from the definition of addition. And the next one is C plus D times A equal to CA plus DA. I will tell you this. All these properties are easy to prove. That is simple from the definition of addition. Let's say, let's prove the first one, okay? So what is A plus B? By the definition, A plus B is equal to Aij plus Bij. Is that correct? But what is this? That is Bij plus Aij. Because scalar addition is commutative. Then, by the definition, again, this is just B plus A. You see, it's pretty easy. And you can prove all the properties, using the same method. Let's consider the following example. So you have 1, 2 plus negative 1 plus 0, 1. So, you can add the first two matrices. In this case, we have vectors, right? So this is 2 by 1, this is 2 by 1, and this is also 2 by 1. So you get 1 minus 1, 2 minus 1, plus 0, 1, and that is 0, 1, again, plus 0, 1. So you get 0, 1 plus 1, that is 0, 2. Okay, it's pretty easy. All right, so for matrices, you have zero matrix. You have zero matrix. What is that? Zero matrix is the matrix whose entries are zero. That's it. Right, you have like zero, zero, everywhere zero. Okay. So this is zero matrix. Zero matrix plays the role of zero in addition. Because, let me write here just zero. Okay. So a plus zero, of course, this equal to a, right? We suppose that a is of the size n by n, okay? So that we can add them. Agree? And thanks to scalar multiplication or even addition, any matrix has additive inverse. Okay, so that means if you have matrix A, then there exists another matrix which is negative A, right, n by n, such that the sum of these two matrices is zero. I write zero of the size n by n. All right, that's it. So that is about matrix addition. So you have different properties in here, and if you pay attention, those properties are similar to properties of numbers. Okay, they are obtained from corresponding properties for scalar additions. Okay, let's consider one more example before we move to matrix multiplication. So we need to solve for the x. We have 3x plus a equal to b, where a is 1, negative 2, 0, and 3. B is negative 3, 4, 2, and 1. From here, I have 3x equal to b minus a, right? So I just write, okay, 3 minus a, b minus a is negative 3 minus 1, 4 minus negative 2, and 2 minus 0, and 1 minus 3, okay? That is negative 4, 6, 2, and negative 2. From here, I divide both sides by 3. I get x equal to 1/3, negative 4, 6, 2, and negative 2. Or if you want, you can write in the following form: negative 4 over 3, 2, 2 over 3, and negative 2 over 3. It's pretty easy, right? Now let's talk about properties of matrix multiplication. Suppose that we have three matrices, A and B and C, such that the matrix product are defined, okay, and C is a scalar. Then ABC equal to ABC. I mean, associative property of multiplication. So in this sequence, you can do product of A and B first, right? And then you multiply with the C, or you can multiply B with the C and then you multiply with the A, okay? The second property is distributive property. A times B plus C equal to AB plus AC. And similarly, you may have A plus B times C is equal to AC plus BC. And if you have a scalar C, so you multiply C with A or C with B, that is almost the same with C with AB, okay? Again, right, those properties are pretty easy to prove, and that is from the definition of matrix multiplication. So we will not do that in here. Let's consider the following example. We have A equal to 1, negative 2, 2, negative 1. B is what? Is 1, 0, 2, 3, negative 2, 1. And C is negative 1, 3, 2, 0, 1, and 4, right? So let's find A, B, and C, okay? Product of three matrices. But look at this. What is the size of A? A has 2 rows and 2 columns, so the size is 2 by 2. B has 2 rows and 3 columns, right? 2 by 3. C has 3 rows and 2 columns, so 3 by 2. If we multiply A with B, yeah, we are good because we have the number of columns in A equal to the number of rows in B, right? And then the product of A and B is the matrix of the size 2 by 3, as we are in here, right? We just pick this number together with this guy, so 2 by 3. And then if you want to multiply this with the C, right, you need to compare the number of columns in AB, which is 3, right? And that equal to the number of rows in C. So we are good. That means, ABC is divided. Okay. All right, let's multiply them. I can do AB first and then multiply with the C. Okay. So let me multiply A and B. That is 1, -2, 2, -1 in here. Let's copy again. 1, 0, 2, 3, -2, 1. I will multiply this, the whole matrix, with the first column, and then I move to the second column, and then I move to the last column. That's how we do matrix multiplication. Okay, there I have the following one. That is equal to the first row with 1, 3. So I will not write in detail. I just write, 1 with the 1 is 1. -2 with 3 is -6. 6 plus 1 is -5. How about that? And then the second row with the first column, I have 2 with the 1 is 2. -1 with 3 is -3 plus 2 is -1. Okay. So I have, and then I move to the next column, 1, 0, -4. So I get 4 in here, right? 1 with the 0 is 0, -2 with -2 is 4. And then 2 with 0 is 0, -1 with -2 is 2. That is the second column. And then if I multiply this matrix, right, with the third column, I will have the third column in here, in the product A and B, right? Let's say 1, 2, and -2 and 1, that is 0. 2 with the 2 is 4. 4 minus 1 is 3. So we have product AB. Okay. Then you can find A and B and C right now. That is just, -5, 4, 0, -1, 2, 3. Multiply with what is C. So I have -1, 0 in here. 3, 1, 2, and 4, right? So you do almost the same thing. You multiply this matrix with each column, right? You have what you need. Okay. This is 2 by 3. That is 3 by 2. So in result, you have 2 by 2 matrix, right? 2 by 2 matrix. So I have to do, okay, let's multiply this, the first column with the first row with the first column in here. So I have -5 times -1, and then plus 4 times 3 plus 0 times 2. That is 5 plus 12 is 17, right? And then the second row with the first column, I have 1 plus 6 plus 6. That is 13. So I have first column. And then I move to the second column. So I erase this. I multiply, the first row with the second column in here. I have -5 times 0 plus 4 times 1 plus 0 times 4. That is 4. Okay, and then I move to the second row. -1 with 0 is 0 plus 2 plus 12. That is 14. So that is the product A and B and C. You see, that is not that, difficult. But the most important is we need to do computation pretty well, right? All right, let's move to one more example. that is just kind of, reminder that the matrix multiplication is not commutative. Okay, let's write it down. The matrix multiplication is not commutative. That means AB is not equal to BA in general. Of course, sometimes A and B are, equal to BA. And for such situation, AB are said to be commutative. Anyway, let's consider the following one. A is 1, 3, 2, -1, and B is 2, -1, 0, and 2. So let's compute AB. I have, that is, okay, I'll do that in my, okay, that is the first row with the first column in here. So I have 2, okay, and then I do the first row with the second column, so I will get the row, right? -1 with 6, I have -5, I have 5 in here. And then I move to the second row, I have 4, and then I have -4. That is AB. But at the same time, you may find BA, so you may need, okay, in case, you may need to write like this. Okay, just write in this order: 1, 3, 2, -1, because I don't want to be wrong. So I have 2 with the 1, -2 with the -1 is 0, you see, and then 2 with 3, 6, 6 plus 1 is 7, 0 with 0, so I have 4 in here, and then I have -2. So basically BA and AB, exists, right? But unfortunately, they are not equal. So by AB and BA are different, the matrix multiplication is not commutative. Okay, I'll tell you this. Of course, if we have the case AB equal to BA, so A and B are commuting. I will tell you this. This is very interesting properties in physics. It's very interesting property in physics. Right now, when we're talking about matrices, we concentrate on system of linear equations, right? We didn't say anything about, applications of matrices in physics, in quantum information, and other things. But, some simple thing like this that makes matrix theory very beautiful. Okay, and that is the the difference, the biggest difference between matrix multiplication and scalar multiplication. Okay, don't forget that. That is the biggest difference, and this is, in my opinion, that's the most beautiful properties of matrices. Okay. All right. So we have one more properties of matrices that is different from scalar multiplication. It says, if you have AB equal to AC, so you cannot cancel A to get B equal to C, okay? Or if you have A, B equal to CB, again, you cannot do conclusion that A equal to C. Don't forget that. In the first one, you cancel this matrix, right? In the second one, you cancel this matrix. But unfortunately, that is wrong. Of course, in some cases, we might do that. I will tell you how, okay? But let's consider the following example. A equal to 1, 3, 0, 1, and B is 2, 4, 2, 3, and C is 1, -2, -1, and 2. Let's find AC. Okay, so what is AC? Let me write 1, 3, 0, 1 in here and multiply with 1, -2, -1, and 2. So I do usual multiplication. I take the first row, multiply with the first column. I have -2. And then the second row with the first column, I have -1, right? And then the first row with the second column, I have -2 plus 6 is 4, and then 2. That is AC, right? How about BC? BC is 2, 4, 2, 3 times 1, -2, -1, and 2. I'll take the first row, multiply with the first column, I get 2 minus 4, which is -2. The second row with the first column, I have -1, right? 2 minus 3. And then I move to the second, -4 plus 8, which is 4. And then the second row with the second column, I get 2. So you can see actually AC is equal to BC, right? Is that correct? But A and B are different, you see? A and B are different. They are not the same. Why AC equal to BC? Okay, so that is very simple example that shows you that you cannot cancel matrix application, matrix multiplication in here. Okay, but look at this. Actually, for scalar, you have very similar properties. Look at this for scalar. 0 times A equal to 0 times B. From here, there's no way to get that A equal to B. You see? No way. If you have A times 0, that is also B times 0. Again, you cannot do conclusion that A equal to B. So for scalar multiplication, you have 0 in here, right? 0 in here. And you might think, yeah, how about matrix multiplication? Of course, if you have 0 matrix times A equal to 0 matrix times B, from here you cannot cancel 0, right? And to get A equal to B. So why? In this case, you see, in this case, C is not 0. C is not 0. Interesting. But you still have a very similar properties. You see? You still have similar properties for like this. You cannot cancel that. So from this example, we may guess that C may have some properties like, okay, let me write here 0, right? Like 0. That means given that C is not 0 matrix, but we cannot cancel, right? We cannot do cancellation. Does that make sense? But look at this. But if this is not 0, so what happened? If that is not 0, we are good. Why? Like if you have A times B equal to A times C, and A is not 0, from here you get B equal to C because you can cancel A just by dividing both sides by A. Or you can say you multiply both sides by A to -1, right? Okay, let me write that step because we will do that for matrices. So if A is not 0, A has inverse, A to -1. Then you multiply both sides by A to -1, right? From here you get B equal to C. Because A times A -1 is just 1, right? This is just 1. Or if you have B times A equal to C times A, and again A is not 0, you can multiply with A to -1, but from where? From the right. Don't forget that. And right here, we multiply by A to -1 from the left, because I don't want to multiply, in this case, okay? I will explain this. Let me finish this first. And then I have C in here multiply with the A, and A to -1. And again, this guy This guy is 1. So you have B times 1, and then here C times 1. From here you get B equal to C. Okay, so that means in case if the A is not 0 and the A is not 0 in here, you may multiply with the inverse of A. And it depends on the position of A. You may multiply from the left or from the right to cancel A out. Okay, why I mentioned this? For scalars, of course, there's no difference, right? Because scalar multiplication is commutative. So you multiply with the A from the left or from the right, that's okay. But for matrices, that is important because you cannot, like A, B, and C, right? You have AB equal to AC. You cannot multiply with the A to negative 1. Okay, right now we don't know what is the inverse of a matrix, right? But suppose that the inverse is X. And that is some kind of matrix which cancels A. Let's say this, right? So let's say A to A negative 1 equal to 1, okay? I want to cancel A. So I cannot multiply, from this side, there's no way. You see? Because matrix multiplication is not commutative. That is not commutative. You cannot just take this to this position. You see? So for matrices, we have to pay attention on the side. So from the left or from the right. Don't forget that. Okay? But again, right? We can cancel if in this case, if A to negative 1 is X. Right now we don't say anything about that, right? But that is some kind of logic. Is that correct? That is similar logic to the scalar case. Agree? We will talk about that later. But I tell you, right? These two properties are pretty interesting. The first case, matrix multiplication is not commutative. So what happens if they are commuting? Right? In physics, that is very important problem. How to classify all commuting matrices. Okay? Because matrices are considered as, observable in quantum physics. But, it's for very special kinds of matrices. Again, right, for this one, yeah, that is very natural to ask the question, for what kind of matrix A we can do cancellation? You see, for what kind of matrix A we can do cancellation. All right, so they are very important, and we will learn that in the next video. All right, so we know zero matrix, right? And now let's talk about a matrix that played the roles as 1. We have 1 times any scalar B, it's just B, right? And if you multiply 1 with some matrix A, that is matrix A. Now suppose that the number of rows and the number of columns in A are equal, okay? Rows equal to the number of columns. Then such matrices are called square matrices. Okay? So in this case, they are square. All right, so for square matrices, you have the following one. A11, A12, and so on, A1n, right? That is general. A21, A22, and so on, A2n. And here is AN1, right? AN2, and so on, ANN. For square matrices, you have some diagonal in here, A11, A22, and so on, ANN, right? For a not square matrix, you don't have that diagonal. Let's say, 1, 2, 3, 4, 5, 6. So we don't see any diagonal in here, right? But if you have one more row, 1, 2, 3, then you have diagonal, because that is square, right? Like, 3 by 3. Okay, so when you have a square matrix, you have the main diagonal. And when all entries on the main diagonals are ones, all the entries are 0, you have the following matrix. You have 1, 0, and so on, 0, 0, 1, and so on, 0, 0, 0, and here we have 1. So all entries on the main diagonals, on the main diagonal is 1, right? Are ones. So this is the identity matrix. Identity matrix. Okay. Suppose that this is m by n. So you might have, identity or, 1 by 1. So you have just 1, right? 2 by 2, 3 by 3, and so on, right? And m by n. So what is the properties of identity matrix? We just consider the case of 2 by 2, okay? Let's take 2 by 2, 1, 0, 0, 1, times with A, B, C, D. That is, like general matrix of 2 by 2. So what do you have? You multiply the first row with the first column, you get A, right? The first row with the second column, so you have B in here. The second row with the first column, you have C, and you have D right here. So what is that? That means, you multiply this matrix A with the identity, let's say I2, right? Let's denote this by n, In. When n is equal to 2, you have I2. That is A. That is, you multiply with the IA from the left. If you multiply with the IA from the right, you have the same, exactly A. Right? So you have A, B, and C, and D right here. So, A times I2, that is A. You will see I2, or in general, In plays the role as 1 in scalar multiplication. Okay, so I can write a sentence in here. In plays the role of 1 in the scalar multiplication. Okay, that is really important for the next section, because in that case you might think about about two matrices whose product is 1. Okay, but we will talk about that in the next section. Okay, so now let's talk about one more kind of matrices, that is transpose of matrices. Suppose that you have A11, A12, and A1n, A21, A22, and A2n, and here is AM1, AM2, and AMN. This is the matrix A of the size m by n with m rows and n columns. So what is the transpose of A? The transpose of A is denoted by A with the T on the top, okay? So that is what? That is A11, A21, and so on, AM1. In here you have A12, A22, and so on, let's say A21, so you have AM2, and so on. You have A1n, A, here should be 2n, and so on, AMN. So what does it mean? That means you just rewrite, just rewrite this row as the first column. You see? So you just rewrite, change, right, the row with the column, right? And then you rewrite this row as the second column, and then this row as the last column. So basically, rows in A will be columns in A transpose, okay? So it says that is the meaning of transpose matrix. Agree? So in this situation, the transpose is of the size n by m. If A is of the size m by n. Look at this. All right, so if we have that, then you can see when you multiply A with the A transpose, what is that? So I can write in here, that is, M by N, and here is N by M. You have a matrix AAT, right, of the size M by M. Is it correct? M in here, M in here. But if you multiply AT with the A, so you get a matrix ATA, and the size of this is different. That should be N by N. Look at this. AT is N by M, right? Here is M by N. So in general, you have N by N. You see? So, transpose matrices are really interesting because you can use transpose matrices to generate square matrices. Okay? Let's consider the following example. Let's say A is 2, 8. That is 2 by 1. Then the AT is 2, 8, right? As rows. So it's 1, 2. And then let's say A is 1, 2, 3, 4, 5, 6. Then the AT would be 1, 2, 3. I just rewrite the first row as the first column, and then the second row as second column in here, 4, 5, 6. All right. So let's find the product of AT and A. Okay. So what is AT and A? That is 2, 8 times 2, 8. That is 1 by 2. That is 2 by 1. So your matrix would be 1 by 1, right? So you have 2 with the 2 is 4, and then 64, you get 68. All right? And how about AAT? AAT looks like 2, 8, and then times 2, 8 in here. So you have 2 by 1. Here's 1 by 2. Your matrix should be 2 by 2. Okay, so I have 2 times 2 is 4, 2 times 8 is 16, 8 times 2 is 16, and 8 times 8 is 64. You see, they're very different. Okay, now let's move to A and AT for the second matrix in here. So let's find AT equal to 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6. Okay, let's write that. So I should have, this is 2 by 3 and 3 by 2. My matrix is 2 by 2 at the end. 1, 2, 3. So I will have 14 here. The next one, 1. This row with this column, I have 1 times 4 plus 2 times 5 plus 3 times 6. That is 18. That is 10. Here is 4. So you have 32, right? I can write 32 in here right away. Okay, I will explain that later. And then the last term is 4 times 4 plus 5 times 5 plus 6 times 6. That is 36, 25, and then 16, right? So 6, 6, I have 7, and then 77. All right, so that is AT. Similarly, you can find ATA, right? You can find ATA, okay? But ATA is a little bit different. 1, 2, 3 in here, 4, 5, 6 in here. Multiply with 1, 2, 3, 4, 5, 6. That is 3 by 2. That is 2 by 3. So at the end, I should get 3 by 3, right? Let's do that. 1/4 and 1/4, I get 17 in here. Okay. So the next one, 1/4 with 2 and 5. So I have 22. 1/4 with 3, 6, I have 27. All right. Without computation, I can write 22 in here. Okay. And then second row with the second column would be 25 with 9, 29 here, right? Here I can write 27. And I multiply the second row with the third column. So I have 6 with 30, so I have 36, so I have 36 in here. And then for this term, I just take the last row with the last column, so I have 9 plus 36, which is 45. All right, look at this. Why I can do that faster than usual is if I have 22 in here, so I have 22 in here. If I have 27 in here, so I should have 27 in here. If I have 36 in here, I should have 36 in here. So what is wrong, or what is interesting in here? If I have 33 in here, so I have 33 in here. 32, sorry. Such matrices are called symmetric. Symmetric. So what does mean symmetric? Okay, let's write that in general and go back to our example. Okay, so if you have matrix A, let's say that is square. Okay, with Aij, A is symmetric if Aij equal to Aji. So what does it mean? That means, you have a square matrix, you have the main diagonal in here, right? All entries that are symmetric with respect to the main diagonal are equal. Okay? Whatever. In any position, right? If you have Aij in here, here should be Aji. And if they are equal for any Ij, then A is symmetric. And surprisingly, the product of A and AT, or AT and A, are always symmetric for any matrix A. So I think we can finish our lecture today. So we'll see you in the next video. If you have any questions, please feel free to let me know.